At 2:46 local time, a mission supervisor in a converted logistics center outside Nerev watches 24 blue markers leave a stretch of coastline and disappear over open water. The display shows nothing dramatic, no explosions, no warning lights, no indication that anything unusual is happening, just 24 symbols moving east at exactly the speed they were programmed to fly. 780 kilometers of ocean separate those markers from the Port Meridian energy complex, a facility responsible for processing nearly a fifth of the region's imported petroleum products. On paper, the drones are still hours away from anything important. In reality, the most dangerous part of the mission begins the moment they leave friendly airspace. Unknown to him, a coastal surveillance radar mounted on a cliff nearly 40 kilometers ahead has already found them. The radar operator initially assumes the returns are weather. The contacts are small, slow, and flying low enough that sea clutter is contaminating the display. He zooms in anyway because the pattern bothers him. Weather does not fly in formation. 24 returns arranged across a front several kilometers wide definitely do. Within 90 seconds, the contacts are classified, forwarded to Regional Air Defense Command, and assigned a threat track. 24 drones, heading east. No transponder, no flight plan, no ambiguity. A coastal missile battery receives the warning while the formation is still beyond visual range. The battery commander studies the track history and immediately recognizes the problem. If the contacts are what they appear to be, then they are too cheap to justify shooting and too dangerous to ignore. The launcher crews receive the order anyway. 3 interceptor missiles leave their canisters within 10 seconds of one another and accelerate out over the ocean. The interceptors were designed for anti-ship cruise missiles. Each one costs nearly $1 million. Each one travels faster than 3 times the speed of sound. Each one contains enough technology to fill several university laboratories. The drones they are chasing consist primarily of composite material, commercial electronics, and a navigation package that would not look out of place inside a civilian aircraft. The exchange makes no financial sense. The battery commander knows that. His superiors know that. Everyone involved knows that. The missiles are fired anyway because nobody wants to be the officer who watched unidentified aircraft cross the coastline and chose not to engage. 38 seconds later, the first interceptor detonates. A bright flash appears on the operator's screen. One drone disappears. The second missile destroys another. The third misses entirely after losing track of its target during the final seconds of flight. 21 drones continue east. Back in Narev, the mission supervisor watches 3 markers vanish from his display. The mission briefing predicted 6 losses before the formation reached the midpoint of its route. Losing only 3 during the first engagement means the operation is currently ahead of schedule. That matters because not all drones in the formation are equal. 15 of the aircraft belong to a group designated Lantern. They are the cheap airframes, composite construction, small payload, limited navigation systems. Their primary purpose is to exist. They fly ahead of the formation because their destruction is part of the plan. The remaining 9 aircraft belong to a group designated Forge. These are larger, more expensive, and considerably more dangerous. Each carries a warhead weighing nearly 80 kilograms. Each possesses an advanced optical navigation system capable of operating without satellite guidance. Each costs several times more than a Lantern. The Lanterns lead because the enemy is expected to shoot at whatever appears first. The Forges trail behind because the enemy is expected to run out of opportunities. 300 kilometers farther east, a long-range airborne surveillance aircraft circles above the ocean at an altitude of 9,000 meters. The radar aboard the aircraft sees the formation almost immediately. 21 contacts. Slow, predictable, maintaining altitude. The tactical commander aboard the aircraft forwards the track to a fighter squadron stationed along the coast. Launching a fighter to intercept drones has become one of the defining calculations of modern warfare. The fighter burns thousands of dollars of fuel every hour. The pilot represents years of training and millions of dollars of investment. The aircraft itself costs more than some commercial office buildings. The targets are unmanned machines built to be expendable. The fighters launch anyway. Because if the drones reach whatever they are targeting, nobody will care how much fuel was saved. 4 aircraft become airborne within minutes. The lead fighter climbs aggressively through cloud layers before leveling off at nearly Mach 1.2. 50 kilometers ahead, 21 drones continue flying at little more than highway speed. The pilot acquires the formation immediately. The radar sees everything. 21 targets, no maneuvering, no electronic attack, no attempt to evade detection. The contacts are flying exactly as expected because they were never designed to survive through agility. The pilot selects a radar-guided missile and fires. The weapon accelerates perfectly. The guidance system behaves perfectly. Everything proceeds exactly according to design. Until the final phase, at the point where the missile should commit to its target, the seeker struggles to maintain confidence. The radar return is weak. The aircraft-sized target it was designed to hunt is not present. Instead, the missile sees something barely distinguishable from the background noise generated by the ocean beneath it. The seeker rejects the track. The missile misses. The pilot assumes bad luck and fires a second weapon. The second missile repeats the performance almost exactly. 2 missiles, 2 failures. 21 drones continue east. If you look here at why the intercept failed, the answer has less to do with the quality of the missile and more to do with the assumptions built into its design. Radar-guided weapons are optimized to hunt aircraft. Aircraft are large. Aircraft move quickly. Aircraft produce strong radar reflections. The filtering systems inside the missile are specifically designed to ignore objects that resemble clutter, because clutter is usually irrelevant. The problem is that the drones resemble clutter more than they resemble aircraft. The missile is effectively searching for a truck and being asked to find a bicycle. Not because the bicycle is invisible, because the system was never intended to care about bicycles in the first place. The pilot studies the telemetry, realizes what happened, and performs a calculation he has never previously needed to perform. He has 4 missiles remaining. There are 21 targets. Even if every future shot succeeds, he does not possess enough ammunition to eliminate the formation. The engagement has already become a losing proposition. He fires one final missile from a different angle. The result changes nothing. The missile loses confidence, abandons the target, and disappears into the ocean. 3 expensive weapons have been expended. 0 drones have been destroyed. The fighter turns away. The formation continues east. Back in Narev, the mission supervisor watches the fighter track leave the display. That aircraft represented the fastest and most expensive interception layer available along the route. If it failed, the responsibility now passes to the next defensive ring. Ahead of the drones waits a network of surface-to-air systems worth several $billions. The commanders operating those systems face a different problem. Their missiles are even more expensive than the ones launched by the fighters. Their magazines are finite. Their radars can see the drones perfectly well. The question is not whether they can shoot. The question is whether they can afford to. 3 hours into the flight, the formation enters the coverage area of the outer coastal defense zone. 21 contacts appear on a command display. Every doctrine manual says engage. Every training exercise says engage. Every simulation says engage. The battery commander hesitates. What he does not know is that his hesitation is about to create the largest gap in the defensive network the mission planners could have hoped for. 3 hours and 19 minutes into the flight, the formation enters the coverage area of the Eastern Shield Integrated Defense Network. 21 contacts appear on the command display of a long-range surface-to-air battery positioned nearly 100 kilometers inland. The battery commander watches them advance across his scope and immediately recognizes the dilemma. Every engagement procedure he has ever trained on instructs him to fire. Every simulation he has ever run assumes hostile aircraft crossing this boundary must be intercepted as early as possible. The problem is that the contacts in front of him are not aircraft. They are small drones whose combined replacement cost is lower than a single missile sitting inside one of his launch tubes. What the commander understands better than anyone else in the room is that missile batteries do not fight wars with range. They fight wars with inventory. Every launch vehicle attached to his battery carries 4 interceptors. The entire battery has enough ready ammunition for 16 engagements before reloading becomes necessary. Against a squadron of fighters, 16 interceptors is a respectable magazine. Against 21 drones, especially 21 drones, that may not even be the real threat. 16 interceptors represents a resource that cannot be recovered once spent. The defensive network was designed during a period when planners imagined fast aircraft, cruise missiles, and ballistic threats, nobody expected to spend multi-million-dollar interceptors chasing composite airframes moving slower than commuter traffic. Yet that is exactly the situation now unfolding on his display. He watches the formation for nearly 6 minutes before making a decision. The contacts continue advancing, they remain low, they remain steady, they remain irritatingly ordinary. Eventually he lowers the handset without issuing a firing order. What he does not know is that this decision creates a corridor nearly 200 kilometers deep through the strongest section of the regional air defense system. Mission planners had expected at least some losses here. Instead, the drones pass untouched. If you look here at what just refused to fire, the Sentinel-X battery represents the centerpiece of the country's strategic air defense inventory. Its interceptors travel at nearly Mach 10 and are capable of engaging targets hundreds of kilometers away. The system was designed to destroy bombers before they reached launch range and intercept ballistic threats during the final stages of flight. Every component inside the battery is optimized for high-value targets. The radar is expensive. The missiles are expensive. Even the trucks carrying the equipment are expensive. What the commander is trying to avoid is spending strategic ammunition against tactical problems. The concern is not merely financial. The concern is that somewhere behind these drones could be a second wave consisting of cruise missiles, strike aircraft, or something even more dangerous. If the battery empties its launchers now, it may have nothing left later when the genuinely catastrophic threat appears. Back in Narev, the mission supervisor watches the formation cross what had been marked during planning as the most dangerous section of the route. 21 markers remain visible. According to the original probability models, only 14 should still be airborne at this point. The operation is no longer simply ahead of schedule, it is outperforming every prediction generated before launch. The advantage lasts exactly 11 minutes. Without warning, telemetry from the lead section begins changing. Navigation confidence drops. Course corrections become more frequent. Several aircraft report degraded satellite reception. Then within less than 20 seconds, every Lantern drone in the formation loses reliable GPS updates simultaneously. The effect is immediate, not catastrophic, but immediate. The mission supervisor has spent years preparing for this moment and recognizes it before anyone else in the room. The drones have entered the coverage area of a dedicated electronic warfare network. If you look here at what just activated the Horizon 12 jamming system, was built specifically to counter long-range drone operations. Instead of attempting to destroy incoming aircraft physically, the system attacks the information those aircraft rely upon. Dozens of transmission sites spread across the countryside broadcast interference on the exact frequencies used by navigation satellites. The satellites themselves continue functioning normally. Signals continue reaching Earth. The problem is that the interference reaching the drones is now stronger than the satellite transmissions they are trying to receive. Imagine attempting to hold a conversation across a crowded room while someone stands beside your ear operating a chainsaw. The person across the room is still speaking. Your ears still function. The information simply cannot compete with the noise. That is essentially what the Horizon network is doing to every satellite signal crossing the region. The first signs of trouble appear among the Lantern drones. Their navigation systems were intentionally simplified to reduce cost. Under normal conditions, they perform adequately. Under severe electronic attack, they become dependent on inertial guidance alone. Inertial systems can continue navigating after satellite signals disappear, but only for a limited time, before small errors begin accumulating into significant mistakes. One Lantern drifts 3 degrees off course. Another begins a gradual turn toward the north. A third overcorrects twice before stabilizing. The mission supervisor watches these changes unfold and feels a familiar frustration. The drones are not malfunctioning. They are doing exactly what physics allows them to do after losing external navigation references. 2 minutes later, the first aircraft disappears from the display. Based on its final track, analysts estimate it impacted open countryside nearly 70 kilometers from its intended route. A second vanishes shortly afterward. A third continues transmitting for several additional minutes before its signal ends abruptly over a sparsely populated valley. The losses are annoying but acceptable because the lanterns were never the center of the operation. The mission supervisor is watching a different group of symbols: 9 aircraft, call sign, forge, the drones that actually matter. Unlike the lanterns, the forge airframes do not rely exclusively on satellite navigation. Their designers assumed electronic warfare would occur and built accordingly. Before launch, engineers loaded each aircraft with a detailed visual database covering the entire route. Rivers, coastlines, rail yards, highway intersections, power transmission corridors, forest boundaries, industrial zones. Thousands of distinct visual reference points stored inside onboard memory. Every few seconds, cameras mounted inside the nose compare what the aircraft sees against what the database predicts it should see. The system does not ask satellites where it is. The system determines its own position by examining the ground beneath it. The difference is the same as the difference between following directions on a phone and recognizing landmarks during a familiar drive. One method requires external information. The other relies on observation. As the jamming intensifies, the contrast becomes obvious. Lantern drones continue wandering gradually away from their intended tracks, while the Forge group remains remarkably stable. Their navigation solutions barely change. Rivers appear where rivers are expected. Roads appear where roads are expected. Rail lines match stored imagery. The aircraft continue updating their positions with growing confidence. What the operators of the Horizon network do not yet realize is that they are successfully disrupting the cheaper half of the formation while barely affecting the expensive half. Hundreds of millions of dollars worth of electronic warfare infrastructure is currently engaged against aircraft that were never expected to survive anyway. Back in the control center, the mission supervisor watches the display settle into a new pattern. 18 contacts remain airborne, 9 Forge drones, 9 Lantern drones. The original formation has shrunk, but the essential striking force remains intact. Ahead of them lies the final defensive corridor, a zone filled with short-range systems specifically designed to solve the exact problem every previous layer has struggled with. Unlike strategic missile batteries and fighter aircraft, these systems were built to engage small, slow targets. Their commanders are not concerned with preserving expensive interceptors. Their commanders are concerned with preventing anything from reaching the industrial complex now less than 70 kilometers away. For the first time since launch, the mission supervisor is approaching a defensive layer that actually wants the fight. The final defensive corridor begins 68 kilometers from Port Meridian and extends nearly all the way to the refinery perimeter. Unlike the strategic systems farther west, which were designed around aircraft and ballistic threats, everything inside this zone exists for one purpose: small targets, slow targets, cheap targets. The exact category every previous layer struggled to handle. At Sector Red 7, a short-range air defense battery acquires the formation while it is still 26 kilometers away. The battery commander has spent the last 2 hours listening to reports from every defensive layer ahead of him. Coastal missiles destroyed only a handful of drones. Fighters expended weapons without results. Strategic batteries chose not to fire. Electronic warfare disrupted part of the formation but failed to stop it. By the time the contacts appear on his display, he already knows something important. These are not ordinary drones. Ordinary drones do not survive this long. The battery commander studies the track data and notices something unusual. Several aircraft appear unstable. Their course corrections are inconsistent. Others are holding remarkably precise navigation despite operating inside one of the densest jamming environments in the region. The distinction matters because it suggests the formation consists of more than one drone type. Unfortunately, he does not have time to investigate. At 170 kilometers per hour, the formation will cross his effective engagement zone in less than 10 minutes. Every decision must be made immediately. The battery opens fire. The first interceptor leaves the launcher and reaches the lead contact in under 12 seconds. The drone disappears in a cloud of debris. A second interceptor destroys another. A third misses after passing just behind its target. A fourth detonates close enough for fragmentation to shred a wing. The damaged aircraft enters a flat spin and impacts farmland several kilometers later. Back in Nerev, the mission supervisor watches 4 Lantern drones disappear within less than a minute. The losses are unpleasant but expected. The Lanterns were built around a simple assumption. If a drone costs less than the missile used to destroy it, every successful interception still consumes enemy resources. The commander of the battery sees the situation differently. From his perspective, 4 kills represent progress. The formation is shrinking, the threat is becoming manageable. What he does not realize is that every drone destroyed so far belongs to the expendable group. If you look here at why the Lantern drones fly ahead of the formation, the answer has nothing to do with navigation or aerodynamics. It has everything to do with human decision-making. Air defense operators are trained to engage the closest target first because the closest target presents the most immediate danger. That doctrine works against aircraft, it works against cruise missiles, it works against almost everything. It also means the first drones entering the engagement zone absorb the majority of defensive attention. The Lanterns are not simply flying in front of the formation, they are spending the enemy's ammunition. The battery commander launches another salvo. 2 interceptors score direct hits. 1 misses completely, a 4th destroys a drone already damaged by fragmentation. The engagement continues exactly as doctrine predicts. Closest targets first. Highest probability shots first. Maintain pressure. Prevent penetration. 5 minutes later, the commander pauses long enough to review the remaining contacts and notices a problem. The drones being destroyed are not the same drones appearing in the telemetry reports from earlier sectors. The signatures are different. The navigation behavior is different. The aircraft surviving the engagement are the ones maintaining the most stable tracks. The realization arrives several minutes too late. The expensive drones are still coming. Back in the control center, the mission supervisor counts 14 surviving aircraft, 5 forged drones remain, 9 Lantern drones remain. The ratio has changed, but the mission is still alive. 23 kilometers from the refinery, another defensive layer attempts interception using a different approach. Instead of missiles, this unit employs autonomous interceptor drones launched from portable catapult systems. The concept emerged from a simple observation. If expensive missiles are economically unsustainable against cheap drones, then perhaps drones should be used against drones. The first interceptor launches from a concealed position beside an industrial access road and climbs aggressively toward the formation. Guided by onboard cameras and machine vision software, it acquires a Lantern drone and accelerates directly into it. Both aircraft disintegrate on impact. The exchange is far cheaper than a missile engagement. It is also far less reliable. A second interceptor loses visual tracking and drifts harmlessly away. A third never acquires its target. A fourth collides successfully. A fifth fails after misidentifying ground reflections as the drone it was supposed to pursue. The defensive network is adapting, so are the attackers. The result is a battle increasingly dominated by economics rather than technology. By the time the formation reaches 15 kilometers from Port Meridian, 12 drones remain airborne, 5 forged drones, 7 Lantern drones. Every surviving aircraft has crossed hundreds of kilometers of defended territory and multiple engagement zones. The refinery now sits directly ahead. Inside the refinery's Security Operations Center, personnel are only beginning to understand what is happening. Reports from air defense units have been inconsistent. Some describe large formations. Others report only scattered contact. Electronic warfare operators insist the drones should have become lost long ago. Yet radar tracks continue approaching. The uncertainty ends 8 kilometers from the target. At that distance, the forged drones begin maneuvering. The course corrections are subtle at first, half a degree, then another, then another. What had appeared to be a single formation starts separating into individual attack paths. 5 aircraft diverge simultaneously toward different sections of the refinery complex. The mission supervisor recognizes the transition immediately. Navigation phase is ending. Target acquisition phase is beginning. If you look here at what the forged drones are doing now, their onboard systems are no longer focused on finding rivers, roads, or railways. Those landmarks were useful for reaching the target area. They are no longer relevant. Instead, the aircraft begin comparing real-time camera imagery against detailed visual models of specific refinery structures loaded before launch. Storage tanks, pump stations, power substations, catalytic cracking units, control buildings. Every drone has its own assigned objective. The refinery appears enormous to a human observer. To the guidance systems aboard the Forge drones, it consists of a collection of geometric signatures, distinct shapes, distinct shadows, distinct pipe arrangements. The onboard computers search for matches exactly the way a person might search for a familiar face in a crowd. The first confirmed target appears on Drone Forge 3, a high-voltage electrical switching yard located along the northern edge of the complex. The visual match exceeds confidence thresholds. The drone commits. No further navigation decisions are required. The aircraft descends. Forge 1 identifies a processing unit responsible for separating intermediate petroleum products. Forge 2 identifies a compressor facility. Forge 4 locks onto a major transfer manifold connecting multiple sections of the refinery. Forge 5 identifies a backup power distribution center. 5 drones. 5 targets, 5 independent attack profiles. The remaining Lantern drones continue flying nearby, still serving their final purpose. Defensive operators attempting last-second interceptions must now decide which contacts represent genuine threats and which represent decoys. The distinction would have been obvious an hour earlier. At this distance and with only seconds remaining, it becomes much harder. One Lantern impacts an empty maintenance area after losing guidance. Another crashes into a storage yard and causes minor damage. A third detonates harmlessly against a concrete service structure. The Forge drones are different. Forge 3 reaches the electrical switching yard first. The warhead itself is relatively modest compared with military munitions designed for hardened targets. The objective is not brute force. The objective is disruption. Transformers rupture. Insulators shatter. Protective systems disconnect sections of the grid automatically. Large portions of the refinery lose power within seconds. Forge 2 impacts the compressor facility less than 10 seconds later. The initial explosion is small compared with what follows. Pressurized gases escape, ignition occurs. Secondary fires spread through interconnected systems. Forge 1 strikes the processing unit almost simultaneously. The damage compounds, not because any individual warhead is extraordinary, but because industrial facilities are networks. Remove one component and operations suffer. Remove several critical components at once and entire production chains begin collapsing. Forge 4 reaches the transfer manifold and ruptures multiple lines feeding different sections of the refinery. Emergency shutdown procedures activate across the site. Forge 5 arrives last. Its target appears less dramatic than the others. There is no massive fireball, no towering plume of smoke. Instead, it destroys infrastructure required for recovery. Systems that would have helped restore operations are themselves disabled. The immediate explosions end within minutes. The consequences do not. Back in Narev, the mission supervisor watches the final telemetry signals disappear one by one. The drones have completed their mission. None are expected to return. Satellite imagery collected several hours later reveals multiple fires burning across the complex. Emergency services remain active throughout the night. Engineers begin assessing damage. Operators attempt to determine which systems remain functional and which must be rebuilt. The mission supervisor finally leans back in his chair for the first time in nearly 6 hours. The operation began with 24 drones crossing a coastline in darkness. 3 were destroyed by coastal missiles. Others were lost to jamming, interception, and navigation errors. Fighters fired missiles that could not reliably engage their targets. Strategic batteries conserved ammunition. Electronic warfare disrupted only part of the formation. Short-range defenses achieved the majority of the kills. Yet 5 aircraft reached the objective. The reason is not that any single defensive layer failed. Most of them functioned exactly as designed. The reason is that the operation was planned around forcing every layer to solve a different problem simultaneously. Cost, inventory, detection, classification, target prioritization, electronic warfare, human decision-making. Every defensive system won its own local battle. The refinery lost the larger one.